So as you can see right here, that flap is open. This flap is not. So if this telescope is a Schmidt-Cassegrain and its focal length, how long it is, the effective focal length is just a little over 2,000 millimeters. That's 6, almost 7 feet. And it has a color camera on that we're going to use to image. So Chris has suggested that we go ahead and I'm going to go right now to something called Iris. And of course, I don't. Yeah, Iris, but NGs, I forget what it's called. The Iris.
NGC 7023.
Yeah. So this nebula, it's actually kind of looks like an iris. That's why it's called the Iris Nebula. And we'll bring it up here and then we'll slew to it and we'll have a look. So, telescope's not connected. Okay. Now we'll slew. So what's happening right now is we can see that the telescope is actually slewing and moving. Yeah. So it's going to well, So what's happening now is the telescope is slewed to where it thinks this object, the iris, is located. It's taking pictures of it, and uh, it, and then it compares with a database the picture with all the stars that are in that surrounding area. If it's not where it's supposed to be, it will tell the telescope to move a little further. The lines are the stars.
Okay, so we are live on YouTube. I only have one camera, so I'm not able to show everyone online what's going on. But Bob's not a great talker, so I'll talk instead. I'm Chris Modnitsky. I'm also with the club. Um, so this is the long, boring part of astrophotography. You're getting everything ready, you're trying to get it set up, and making sure everything works. So once everything is set up, which can take a while, the very first thing you do is you start finding your targets. So the telescope doesn't always point exactly where you want it. So this is called a plate solve. It just takes a picture of the stars and then figures out, compares to a database and then figures out what it actually is pointed at. And the neat thing about today's systems that are all computerized, it'll correct it for you. So it'll realign it to where it should be. So this is similar to the type of telescope that we have out there. Not exactly the same. That one I think is a little bit bigger. This is the 8-inch version that we have out here. And again, people online can't really see. That's fine. Pretend. And I will take off the dew shield in front because this will make it easier to understand what's happening. Okay. Normal telescopes. Every telescope that you grew up, there's a lens in front and there's an eyepiece in the back, and you look through the eyepiece at whatever the target is, right? Or sometimes if you have a Newtonian, there's an eyepiece off to the side near the front. This is a dedicated astrograph. It is a telescope that is only for taking pictures. There is no place for you to stick your eyeball on this thing to see. At the very front, there is the camera. In the very back, there is a mirror. So the light comes in from the front, bounces back up, so it hits the mirror in the back, bounces here to it's like a lens assembly. It takes the light and compresses it and focuses it properly and then sends it to the camera. So once it's at the camera, we can start imaging. So the telescope we have out there is just a bigger version of this one. And again, there's no place for you to put an eye. I mean, even if you put your head in there, now your head is in the way. So the way the telescope is set up, the camera in front doesn't really affect the image too much. As long as it's symmetrical, as long as your cables are relatively out of the way, it's fine. It works, okay? With Newtonian telescopes, with like the big telescopes, if you look at Hubble, it has a mirror in front as well. James Webb, it has the three big, the big tripod out in front, and then there's a mirror assembly there, or is it the camera assembly? I think it's whatever it has right there and sends the image back down. Whatever's in front of the mirrors is out of focus. So it doesn't really appear except as what we call diffraction spikes. It's a quantum mechanical effect that the light bends around the spokes of the secondary holder, or in this case, what's holding up the camera. So it's why when you're looking at Hubble images, all the stars have a big cross across them. So it's just a quantum mechanical effect. It doesn't really change much of the data, and a lot of people find it pleasing. So that's why we have it. That's why we leave it in. So right now, do you have something?
Nope.
Nothing. It's still slewing? It looks like it's still slewing.
It's plate solving.
It can't plate solve off of that.
Yeah.
So what you're seeing right now, these streaks of light, those are stars, and it is just not able to see. It can't do a plate solve from the streaks. It is now 6:56. It's almost 7 o'clock. Don't feel too bad. A couple of weeks ago, I was trying to do imaging. I had so many problems, I didn't even take my first picture until 11:30 at night. Something like that. It was about 11:30 at night. I got really frustrated, and then I was exhausted by about 12:30 and just went right to bed. So there are nights like that.
So what's in the image that's displayed right there right now?
The background image, that is from the star chart. So we can use a star chart connected to the telescope, connected specifically to the mount. So this down here, this is the mount. Okay, this is what actually moves around and points. The telescope's only job is to gather photons and compress it to a small place so you can either see it or you can image it. That's its only job. The mount itself is what does the tracking. You have to align this to polar north. So for example, this one is aligned so that this axis here points towards Polaris, but not exactly. We want to point it directly at the celestial North Pole, which is a little bit off of Polaris. There are lots of ways to do it. The systems now, you can do it computerized, and then you fiddle with the knobs here and here, and there's a knob in front, and you get it just right until the computer tells you, yeah, this is fine, this is now polar aligned. And once you have that, you do a star alignment. So you point the telescope at 3, 4, 5, 10 different stars, and now the mount knows this is what I'm pointed at when I'm in this part of the sky. So now it knows. Once you have that, then you can go through and start imaging. So the star charts here, they get data from the mount. The mount is actually sending information. I am pointed at, sorry, let me rephrase that. I think I'm pointed at this. You then verify it with the telescope, the camera, take an image, do the plate solve, then the software sends a signal back to the mount saying, yes, you are pointed at what you think you're pointed at, or no, you're pointing at something completely different. Let's resync you to what you should be pointed at. So in the star charts, you have a nice little marker saying, I'm pointed at this. This is my center point. And you can agree or you can disagree. And if you disagree, you have to resync it.
So the map has the computer on it and the telescope has the camera on it.
Yes. The mount has, this one in particular has two computers. There's a computer within the mount and there's a computer within the handset. So the mount knows what to do. But the mount at that point can only be controlled remotely from a computer. If you plug the handset in, all of a sudden, okay, it knows where all these objects are, and it gives you an interface at the mount that you can now play with it. You can do everything manually. You can slew left, right, or up and down, essentially. And then you can say, oh, well, I'm going to look at this object, and you punch out that object, and then it'll go find it. The nice thing about today's mounts, it used to be that you had to have your star charts next to you, and you had to know exactly what you wanted to look at in terms of its designation. So we have a bunch of different catalogs. Our catalogs are lists of objects. That's it. And they're named after, well, most of the time they're named after someone who spent the time years and years ago figuring out what these objects are, or at least, hey, there's something weird here, and then just marking the location down in the sky, the right ascension and the declination. Right ascension, think of it as the equator going around, so you have 24 hours. And then the declination is how many degrees north or south of the equator. So that lets us map anything in the celestial sphere. And you have catalogs. So the very first catalog that we have is the Messier catalog. And Charles Messier was a Frenchman who cared about comets and absolutely nothing else. That's all he wanted. But he kept finding all these objects in the sky that were bright, they were fuzzy, they looked like they could be comets. Remember, back then the telescopes weren't that great. So everything was kind of a fuzzy blob except for stars. So he would find all these fuzzy objects. It's like, oh, that's a comet. And watch it night after night after night, and they didn't move. So he'd mark it down as, this is not a comet, this is not a comet, let's ignore this, let's ignore this. And as time went on, he and his assistant found 110 objects that were not comets. So his catalog, he would send this out to fellow comet hunters saying, hey, if you see this, it's not a comet, you can ignore this. But the Messier catalog now is 110 of some of the most interesting objects in the sky. These are bright nebula, these are galaxies, these are globular clusters, these are open clusters. There's a binary star in there somewhere. But these are interesting objects that you can see with small telescopes. It's the Messier catalog. So if we want to look at the Andromeda Galaxy, it's Messier 31. So on these old handsets, you would type in Messier or M31, and the telescope would go, okay, well, I know where I'm at right now, so let's move over to where you want to see. But you still have to have your catalog with you to know what you want to look at. So we have the Messier catalog. We have the Abel catalog. We have the Caldwell catalog. We have the New General catalog, which is thousands and thousands of objects. And again, these are galaxies. These are nebula. These are open clusters. These are globular clusters. There are all sorts of things. And most of the objects in the NGC catalog, it's not just one designation they have. Sometimes they have multiple ones. So Andromeda has a Messier number, and it has a New General Catalog number. So you can use either of those to get to it because the system knows. And then there's stuff which, like, I think there's Able 2, which I was imaging a couple of weeks ago. And actually, I was imaging a completely different nebula. I was imaging the Pac-Man Nebula, and way over to the side, I noticed a little bitty, tiny, little bitty blue round thing. And I was like, oh, well, that's interesting. Let me go back to the catalog. And it turns out this is a planetary nebula that's in the same general region, which I didn't even bother to see, and it doesn't even show up on my software. Wait, hold on. No, it did. It did show up on my software here. It didn't show up on my software on my phone because it's so small. It's just a little bitty blue thing, but you can still see it. It's still visible. And it was there way off to the side of my image. I wasn't intending to get it, but there it is. But this is so small that it doesn't even have a New General Catalog number. It's just Able 2 after the guy who found it. So, any luck? Oh, I don't even remember. This is number 2. I think there are a couple hundred. There's like the Caldwell catalog has a couple hundred as well. Barnard. I think it's over 100, but I don't remember. Yeah, I don't memorize these things. That's why we have catalog. That's why we have books. That's why we have software. We don't need to memorize this stuff anymore. It used to be you would memorize like the ones that you needed to work on, especially if you were an astronomer. The Messier catalog, it's fairly easy to remember. It's only 110 objects. But some of the stuff, like all these galaxies, there are tens of thousands of galaxies in, well, let's see, is it over 10,000? It's well over 10,000 objects in the New General Catalog. A lot of them are galaxies. There's no way I'm going to remember anywhere near all of them. I don't even remember. The only NGC object I can remember is NGC 7000, the North American Nebula, because it's 7,000, it's really easy to remember. The others, I don't remember. I always look them up. So this is what the Iris Nebula looks like, and this is part of a larger complex. The Iris is part of an open cluster, and the Iris Nebula itself, it's a reflection nebula within the cluster. So we have a couple different kinds of nebula. We have bright nebula, we have dark nebula. And then under bright nebula, we have reflection nebula, which is usually it's that bluish color or sometimes yellowish color. It is literally dust that's reflecting the light of the stars in the region. That's it, it's all doing. It's all it does, it just reflects the light. An emission nebula is a nebula that glows. So typically we see these in stellar nurseries, like the Orion Nebula. So we have young, hot stars. And young stars are big, they're bright, and they're blue. Most of their light is towards the blue and ultraviolet end of the spectrum. So these are young, they're going to burn out very quickly, they're putting out a whole lot of light in the ultraviolet, and they are causing all the gas around them to glow. So if it's hydrogen that's getting this ultraviolet light, it is glowing red. If it's oxygen, it glows this bluish green color. If it's sulfur, it glows a slightly different color red than the hydrogen. And we can pick out these colors. Now, with our eyes, looking through a telescope, all we see is gray. Our eyes are not sensitive enough to see color through most telescopes, especially small telescopes like here. If you want to see color in a nebula, you need something big, like one of the scopes out at Fort Davis. I think they're 86-inch scope. On some nebula, you can start to see a little bit of color. There's the Ring Nebula. The Ring Nebula is a planetary, so this is a star that, at the end of its life, blew off its outer layers, and so there's hydrogen and oxygen gas surrounding the remains of the star, and the remains it's just the hot core, the leftovers of the star, and it is no longer burning or fusing hydrogen. It is glowing from the residual heat and throwing off a lot of ultraviolet radiation. And it will slowly cool down over billions of years. It takes a long time to cool down in space. So the ultraviolet light, again, is causing this gas around the star, or the white dwarf, the remains of the star, to glow. The hydrogen glows red, the oxygen glows blue-green, and with a big enough telescope, we can see that. Now, for imaging, we don't need such a big telescope. This one does just fine. And so we can see the color in the nebula after just a few minutes of imaging. Any luck, Bob? Not yet.
Can't guide yet.
Yeah. Sometimes this is just what it is. So with the emission nebula, they glow in colors. With the reflection nebula, they just glow with the light of whatever stars are in the area. They reflect. And then the dark nebula are bands of dust. And can you bring up that image of the iris?
Pardon?
Can you bring up the image of the iris from the catalog?
I think we're in good shape. Let's try this.
Think it
one.
better?
Yeah, the flap opened on the guide.
Oh, okay.
Yeah.
Oh, there we go. So what we're seeing right now, this is a guide scope. So this is that small telescope that's on top. That's basically the same thing as this right here. And there's a small camera connected to that telescope, and it has one job and one job only. It finds a star, and it locks onto it. And this software is called PhD-2. PhD does not stand for anything related to a doctorate. It stands for Push Here Dummy. That's what it stands for. And what it does is it locks onto the star, and it teaches itself by sending pulses to the mount to move in different directions. So it'll send a pulse go north. Tell the mount to go north. And the mount moves in a particular direction. It monitors the star, and then it says, okay, if one pulse moves it this far, and 2 pulses moves it this far, and 10 pulses moves it this far, I know which direction I need to go for north, which combination of pulses. And then it does it for all the cardinal directions, and at that point, it's calibrated, it knows what to do, and now it can lock onto a star and keep that star exactly centered. And that means that the image through the big telescope will not have star streaks in it, ideally. Okay, what do we got?
Nothing quite yet.
Nothing. Okay, can you bring up the Iris Nebula?
The what?
The Iris from the stellarium?
I have something better.
I was going to look at stellarium.
I'm sorry?
I wanted you just to bring up stellarium.
We don't have stellarium.
Oh, what were you looking for? I thought you had the... Okay, so I don't know. This is Bob's system. My system is a little bit different. I like to think my system's a little bit simplified, a little bit more streamlined. But I keep my stuff in the backyard. And I will say that doing a little bit of automation and not having to be outside, being able to be indoors, especially when it's really, really cold, it makes so much of a difference. the iris? Okay. Slowly. Okay. So what we're seeing here is the reflection in the dark nebula. So the reflection is all in blue, and everything that looks grayish, brownish, black, that's the dark nebula, the dust bands. So the dust is actually blocking out the light from behind. That's all that it is. That's why it looks dark. And what we can actually do, and remember, this is visible light. This is regular visible light, what you and I can see. But if we use an infrared camera, or specifically an infrared telescope, we can actually cut right through that dust and we can see the stars behind. And we can see this thing with like the Horsehead Nebula. I don't know, does anyone know what the Horsehead Nebula is? Have you ever seen the Horsehead Nebula? No? Oh boy. Okay. The Horsehead Nebula is a really, really famous one in Orion. It is near, it's right off of Orion's belt. It is really hard to see with the telescope, especially in the city. But if you get out to a dark sky site and you put on just the right filter that'll block out everything but a very narrow bandwidth of light, you'll be able to see it. And we call it the Horsehead Nebula because it literally looks like a black horse's head up against the background light or from the nebula. And it is a dark nebula. It's just a region of dust. There we go. So there's the Horsehead and the flame. So the Horsehead, well, it looks like a horse's head. And the flame looks like a flame on its side. But they only have the shapes because of basically negative space. It is a dark band of dust that's blocking out the light from behind. And in fact, if we were in any other position, the nebula would look completely different because now the horse's head will not have the same orientation because it's a blob of dust. And for the flame down below, it will not look the same because, again, these are just dust veins in a particular pattern, in a particular formation that's only visible from where we are right now. And around this star, or actually a couple of the stars here, you can see greenish and bluish kind of clouds, and those are reflection nebula. So it's dust around those stars that's just reflecting the light from them. And PhD, it's connected. Is it not connecting? Yep, so now we do, okay, you got stars. And guiding, okay, cool. Uh-oh, do you have to calibrate? Bob, do you need to calibrate?
I don't.
Because it's going way off. Oh, well, there it goes. Now it's coming back. Okay. All right, as long as it's figured out what to do. Nope. Yeah, I don't think it's calibrated. If it is, that is way off. All right, we're still figuring this out.
I'm sorry?
We're still figuring it out. Is the imaging camera ready?
Yeah, we're just, I think we, like you mentioned, we might have a guiding.
Yeah,
problem.
I would just stop guiding and let's just do 30-second unguided and see what we get.
We're not gonna get anything.
Why not?
So,
Uh-oh. Yeah, I think the calibration is off. And this happens. I had a mount was it last week, that I could not get it to calibrate very well, and I just started doing unguided images. where the mount was doing the tracking. I didn't have to worry about the camera. And it actually worked. I was able to take 4-minute subs. Wait, is the main camera not working? Hey, Bob, is the main camera not working at all?
Main camera is working, but without guiding, we're gonna get star. Okay,
But we're not doing, wait, is this with a Hyperstar at F2 or?
no, not.
Oh,
Hang on.
yeah, again, this is the boring part of astrophotography. Is it still cloudy outside? Is it still cloudy outside? Has anyone looked?
He came here and said, we could go out there and look at Saturn.
Go for it.
So I think it's probably clear enough or something.
If it's clear enough, go for it. We've had clouds all day here in Dallas Fort Worth and rain early this morning. And we have some telescopes outside right now. So there are people doing observing. And in the meantime, we're trying to get this working. We did run one test of this before, and it seemed to work then. But apparently not terribly well right now. Hey, George is saying we might need to power cycle the USB hub.
I'm talking with Jim, his mount.
Okay.
Okay. And then power down the mount. Okay. Give it. Okay. Can you, who all's on the YouTube at the moment?
Oh, we have 11 people watching right now. George is on. Hi, George.
Is, someone by the name of maybe Sri Sanaka?
I would have no idea.
Oh, okay, just,
You can always ask if they could jump onto the chat.
oh, I forgot I had a microphone in
Yes,
front of
the
me, so,
microphone's been on the entire time.
Begin alignment. We're having just issues with the mount. We're getting it sorted out as quickly as we can. Begin alignment.
Remember, everyone can see what you're seeing.
Yeah,
And they can see you too.
I hope I'm not breaking any cameras.
Don't pick your nose.
Move to switches.
Okay, we managed to get our internet connection back. We're looking at Jupiter right now, and we can see some of the banding on Jupiter.
Okay, that's awesome. Okay, so that works. All right.
And our guiding is working, so we should be able to start to do imaging now. Sorry about that, everyone. Yeah, we're back online. So,
The video is up and running.
yeah, we're able to actually get online. So we had an issue with our internet connection where it just dropped out on us. So finally managed to be able to get it back online. Had to reset the Wi-Fi adapter.
That's bloody awesome.
All right, and the telescope is a Celestron 11-inch Schmidt-Cassegrain. I think we have the focal reducer on here. Is this hey Bob?
Yeah.
Is this a HD?
No.
This is the old one. Okay, so if it's a focal reducer, it's a 6.3 DF 6.3 Celestron focal reducer on it.
That's not bad.
And yeah, we can see banding.
So do we want to disconnect the camera and try SharpCat real quick? Okay, we're going to try
Okay,
an image Jupiter
okay.
in SharpCat.
And we can do a smaller ROI on it,
Exactly, yep.
so we can get faster imaging. Okay, cool.
So I'm going to the camera, disconnecting the camera, and I'm going to do SharpCat.
Yeah, it's never fun when the internet connection drops out. I had the same issues for my house where I have a very, very lovely network, a really fast mesh network, but for some reason outside it just could not maintain the connection to my laptops. So I ended up actually just running a network cable from a switch outside that I plugged all the computers into, and then ran the network cable through my window, or actually under the window, and plugged that into one of my mesh routers. And once I was able to do that, then I could maintain a connection out to my machines. And it was very, very nice to be able to do remote stuff. Okay, so what we're looking right now is this is SharpCap. This is a different application. I think you need to make the ROI much, much bigger so we can find it.
So now it's not showing up that.
Yeah, Bob, change the capture area. You need to make the ROI much bigger.
Okay, I'm trying to get their capture area
Yeah.
Okay. ROI. Oh, there it is.
No, that's panning. Go up above where it says
Yeah,
capture area
where
selected.
that is. Oh, start capture.
Okay. No, you're fine. You're fine. You're on live view. You have to change. Now I'm gonna have to get in the frame where it says there, select ROI, apply ROI. You change that, make it full. Go to the full one.
Which
No,
one?
but yeah, pull it down. Go to to the very top. So scroll up. Take the big one. Yep.
Okay.
Okay. Now we get the whole thing. And change your time.
Yep.
No, that's way too. You've got to do like change it to 1 second.
Oh, okay.
No, that's do the quick picks. Pull down the quick picks right below you.
Hmm?
Quick picks. Quick picks. Where is it? Right there.
Oh,
That pull down, and then take it to 1 second. And over here, zoom is 300. Change
Oh.
zoom to auto. And now we can actually see something, hopefully.
go.
There's Jupiter. So it is,
wow, I think we might have to,
why is it black?
because I may have the wrong setting. Hang on a second.
Okay.
We are guided, we're guided
Yep.
well, actually. All right. Yeah, we are. Yep.
Okay, now go to zoom in.
Um,
Oh. Switch it to RAW 16 for the
Raw 16,
RAW 16.
okay.
It's probably black because it's blown way out, which is
Okay.
fine.
So,
Then cut the exposure down to half a second. Use the quick picks. Quick picks is your friend. I think you've got something set for, okay, let's do this. Do you mind?
yep,
All right. Hello, everyone.
Chris is gonna get this.
All
sorted
right,
out
yeah,
for us.
let's figure out what's going on down here. Thermal controls on, hey, let's get that colder. So turbo, maximum frame rate. Let's go to the top. Get rid of, they just do fits. We're not going to be doing any recording right now anyway.
No.
ROI, that's fine. We're not doing any binning, that's fine. Frame limit, turbo. Where is my gain? Ugh. Change this to 100 because this is, yep. So 100 is unity for,
This is a 071.
yep. So pre-processing, let's see what we have under pre-processing. Nothing, none, that's fine. We can do background. I like this one. Seems to work really well. Scope controls, oh, here we go, that's why. Why is it black? We are not dealing with an eclipse here. Yeah. Is that, I wonder if there's a, let's see. Let's go way down, 30th of a second. There we go. Okay, so black is blown out. Okay, so let's do less than 30th of a second. Let's do, there we go. Now we're seeing some details. There we go.
There we go.
But I don't like, ugh. I don't like how chunky that looks.
Well, again, this is 071, so it's not planetary camera, is it?
Doesn't matter.
Oh,
At RAW 16, we should be able to see something a little bit nicer. I wonder what the color space is. Let's do this. Yeah, that's not nice. Yep. Over bright. Let's just do this because it's planetary. Let's get something quarter second. There we
that's
go.
better.
That's much nicer. Oh, there we go. Now it's clearing up. So let's say you do live stack. before we do, you know what, before we do live stack, let's turn off live stacking. Oh boy. Yeah, we're getting way too many images coming in. Okay, let's turn off live stacking. And because this is centered, uh-oh. We're going to select an ROI, and let's get something smaller. There we go. So this gives us a much smaller ROI, so we can see Jupiter pretty
Okay.
decently.
Yeah, it's not bad.
Yep.
We haven't run autofocus, so
No. Oh, we haven't?
no.
Oh, now you tell me. Okay. You know what? I don't think we can do live stacking on this thing. It's not going to work, planetary live stacking.
Okay.
Yeah, it's not going to work. Or at least it's not going to work well because we are remote. So if we zoom in, yeah,
Okay.
it's not quite in focus, but we can actually see a little bit of color.
Like maybe here.
You can, but I don't think it's going to make much of a difference. Remember, we're sending over data, like screen data, over a Wi-Fi connection, over a VPN. Well, connection out there and then a VPN. So this isn't going to be the same as being in front of the computer. There is some latency between what we can see and what we're doing out there because it's remote. But it's not too bad right now. So we're able to see some of the banding. And there's that cutoff.
See, what I plan to do for
There's if you look really pretty close where the cursor is, it looks like there's like a missing chunk out of that, the band on the left. I wonder if that could be, I don't know if that could be the Great Red Spot or not. I don't know if the Great Red Spot is visible right now, but I will bring up my deal and see if it is. Okay. Okay. All right. Cool. That works. All right. I am jumping onto my software on my phone so I can see just where the Great Red Spot is. And I wish I could do it from here, but I really can't because I don't have everything set up the way I want it. Ah.
I think we have to do some settings for this.
Yeah.
Live stacking.
I wouldn't, Bob, I wouldn't mess with the live stacking for the planetary.
Yeah, I'm not.
Yeah. Just turn it off. Okay, so let's look at Jupiter. I see Neptune, Saturn, Uranus, Venus. Look along the ecliptic. Uranus there is Jupiter. So sorry, it can't see it on there, but I'm looking at my phone and I don't think that's the Great Red Spot. What we're looking at is hey Bob.
Yeah,
Could you turn off and go back just to the regular view?
regular view.
The regular view. Yeah, turn off the live stacking.
I thought I did.
No, you didn't. You got to hit this X right there.
Oh.
Yeah, there we go. That gets rid of it. Okay, so this little space right there,
Uh-huh. Oh, is that the right spot?
no, that's not the red spot. That looks like it's a possible one of the white spots. It's hard to tell at this orientation, but what it looks like is the right is Jupiter's north, and the left is Jupiter's south. So it would be in that band. The Great Red Spot is in the southern hemisphere of Jupiter, but I don't see the Great Red Spot. But in that spot, I do see a possible white spot. So there could be a storm, a white, basically a white hurricane, instead of the Great Red Spot in that area.
This is awesome.
So what we're looking at right now is Jupiter. And one of the neat things is with imaging planets, That's the best way to describe this. We use a thing called lucky imaging. And lucky imaging is basically taking a lot of images of a planet or the moon, and then you record them all. So, for example, we would take a movie, and we may take 10,000 frames of Jupiter for, I don't know, just a few minutes. And we want as fast as we can. We want the shortest exposures we can, and absolutely as fast as we can, and just record to the hard drive. And we take that movie and we process it, and we have software for that. And we process it, and what we want is only the best of the images. We want the best 1%, we want the best 2%, and throw away everything else. Once we have those, we can stack them. So think of it like putting in like the layers of an onion. And this gets us more and more data and better data than we otherwise would be able to get. And by just taking the best 1% of images, and those 1% may only be 20, 40, 50, 60, 100 images instead of several tens of thousands. But those best 1% are going to be the clearest images. So we have some of our club members who've come back inside, and there we go. Okay, so every few moments, every 15 minutes, every half hour, maybe sometimes a little bit longer, we see the atmosphere will stabilize, and then the image becomes really, really good. Okay, that's fine. You can turn on your microphone too, you know.
Okay, well, we're going to move off to Saturn, and then we're going to go to a surprise planet. Kids will love it.
Take this, this way. I've switched the mic to a slightly different setting so that we can both talk.
Okay, awesome.
Because I don't like dead air. No one
Okay.
likes dead air.
All right, so I'm going back. I'm using a tool called Nina. This is our tool that we use to image with. And since I use Nina for everything, I'm reconnecting the main camera. And now I'm going to go to my imaging control area. And we're going to head over to Saturn. So this is essentially getting the information about Saturn loaded. And now I'm going to tell it to go over, put it in my framing component, which allows me to frame what the image is going to look like. So this is the size of the frame of the particular camera that we're using, and we're using a color camera today.
Bob, why are you looking at the microphone? The camera's out there.
I'm sorry?
Talk to the camera, don't talk to the microphone.
Oh,
The microphone will pick you up.
okay. So what we're looking at right now, this tool that I use to image with is strictly for deep space objects, so it doesn't know anything about planets. But I know that in theory that Saturn is going to be in the center. This box here is the frame from the sensor on the camera. So it's telling it right now it's at this angle. So I'm going to go ahead and tell my mount to slew and center. So what happens now is the mount is moving. If I can be quick enough to get to. So we can see that the mount is now moving to where Saturn is. Okay. And what's going to happen is once it gets to where Saturn is in the sky, it's going to stop slewing or rotating. And then Nina will take a picture and it will compare the location of where it physically is with where it thinks it's supposed to be, and it will make minor adjustments until everything is centered. And then what we can actually wind up doing is determining the actual rotation of the camera. Saturn is getting to be pretty low, so we like to watch where the uh, the mount is because we don't want it to go below uh, the clamshell here. So now we're going to go back to Nina. And it's taking a 15-second exposure. And Saturn is this very bright thing right here in the middle. And it's so bright because it's overexposed. 15-second exposure on a planet is very high. So what this bit is telling us is that we're off by quite a bit. So we have our tolerance set to less than a degree. I actually think it's set to less than a half a second or half a minute, 30-second arc, 30 arc seconds, which is half a degree error. So it's taking another image, it's comparing it, and we should see the total error change, which it is. So so it's doing a minor slew right now. And we could be looking at it, but the slew is so minute that we would not see it. And the reason why we have this big donut here is because Saturn is well overexposed. And we're pretty close.
You know, Sharp Cap can do the same thing. Sharp Cap is fully capable of doing the plate solve, figuring out what it's pointed at, and then doing a sync back to the monitor or to the mount.
But I don't know Sharp Cap.
Ooh. I am here to teach. Remember, it can be close enough. It doesn't have to be perfect.
Yeah. I think we're getting there.
And usually for my stuff, if it's in the field of view and it's close to the center, it's good enough. It doesn't have to be absolutely perfect. Perfection is the enemy of good. Chase perfection all night long. Never quite get it. But if it's good enough, it's good enough. As we say, we'll fix it in post. Jim is on. Looking at it, he's describing the machine, or the telescope. Says it is a C11 with the F7 focal reducer.
So now we're going to find out what our rotation angle is. Not that it makes any difference for planetary, but for our deep space objects, we may need to make adjustments.
No, we don't.
I do.
That's why I say we fix it in post.
Yeah. So this is the actual rotation angle.
I did some imaging of some object. I can't remember what it was. And I actually had someone complaining about it, saying that's not the correct orientation for that object. That's not the standard orientation for that object. Well, so what? I mean, if you're looking at it through any telescope, even naked eye, it changes its orientation through the night. So take a look at Orion. If you look at Orion, when it is on the eastern horizon, just rising, Orion is on its side, where uh, Betelgeuse is to the lower left, and then Orion's belt is in the middle, and it looks like Orion is lying down. But then, as it crosses the meridian, as it goes overhead, now Orion is standing up, and Betelgeuse is now the upper left shoulder, with the belt going across the middle, then going down to Rigel to the lower right-hand corner, the foot, and its orientation has changed. So if you're looking at the Orion Nebula through a telescope, its orientation changes as well. A little bit more exposure. Okay, a little bit less exposure. And we can barely
You
see the ring
rings.
because we are almost edge on to the
Yeah.
ring. There we go. That ring is very, very faint. Bob, if you can scroll down. No, this way. Here. Scroll all the way down. Keep going. Keep going. And click on the red. Okay, and click on the one below it. There we go. So now this is blown out. We can make out the ring. And the neat thing about the ring this way, we can actually make it out when previously it was very, very dim. Because of our orientation to Saturn, our view of the rings go through a cycle where sometimes we see them not quite fully face on, but they're really, really wide and very easy to see. Right now, we're going towards Saturn's ring disappearing. And we will get to a point where for, I think it's like a couple of weeks, Saturn's rings will virtually disappear. Not for very long, maybe only a week. It's not very long at all. But we will only be able to see Saturn. At the most, there'll be, with a really, really good telescope, you'll be able to see just a line, a very, very thin line where the rings are. The reason is the rings are very, very, very thin. What I mean by thin is we think they're only about, I think it's like 10 meters, 10 or 15 meters thick in most places. That is not very much. That's, call it 30 to 50 feet, maybe. So these are ice particles. They're smaller rocks, sometimes a little bit bigger rocks. We have some shepherd moons in the ring system, but the rings themselves are very, very thin. I guess we would describe it that way. So when we get edge on to the rings, they pretty much disappear for us because we really can't resolve something 10 meters wide at our distance from here to Saturn. But as soon as that's over, the rings start appearing in a little bit different orientation, and now they appear to be growing and getting wider and wider just because we're changing how we're looking at it. And then they get brighter and brighter and brighter, so we see more of the rings. So right now, Saturn is a little bit underwhelming because the rings are almost edge on. But we can still make them out.
Okay, so let's try. Um, mm,
Want to jump onto Orion?
to what?
Orion.
Orion, well, I was thinking about going to, well, we'll do that. We're not quite there yet. Orion, where in Orion do we
M42.
want to, M42?
Yep, it's in the same general area as Jupiter. Check my star maps. So it's pretty low. It's pretty low, but we can take, yeah, we can take some short exposures and we can look at the core. So we won't see the full glory of the Orion Nebula only because it is a very large target, but we can look at the core at the trapezium.
Okay, yeah, that's a great idea.
So change your ROI back to Mondo Big. X. ROI is above it. Yeah. Yeah, change that to full. Change your zoom. The zoom is auto. That's good. Okay. So now you should be able to slew to the Orion Nebula. So this is a dedicated astronomical camera. It is a cooled camera. So it has a neat little, it's called a thermoelectric cooler. And you see these in portable refrigerators that you have in your car that plug into your 12-volt power socket. They also make these for wine refrigerators because they are very, very quiet. And this is a semiconductor cooler where one side, when you flow power through it, DC power, one side gets really hot, the other side gets really cold. So you slap a fan and a heatsink onto the hot side to take the heat away, and the cold side gets really cold. So you put that cold side up to the chip on the opposite side of the chip from where the light comes in. It cools down the chip and it reduces the heat noise to the chip. And if you reduce the heat noise, you get more signal. If you get more signal, now you can get more data. You can actually see what's going on. You can see more nebula. You can see dimmer stars. You can see the dimmer galaxies. Right now, the telescope is slewing. It is moving towards the Orion Nebula, away from Jupiter. Hopefully, it won't hit the camera.
Well,
The line, it's coming right for us. This is one of the neat things about automation is we can actually do this kind of stuff now. A long time ago, we had to have operators right at telescope. Oh, nope, yep, doors unlocked. Hello. We have an audience here at the YMCA.
but camera connection lost, that's not good.
Well, use Nina just to move it. Don't do any imaging.
Thank you
That's
for
what funny
coming.
putting up the telescope to have dew on them.
Oh,
So,
yeah.
Thank you. It was fun.
You're welcome. Have a good night.
You too.
Drive
Thank
safe.
you.
That's interesting.
Yeah, I would just don't mess with Nina for the imaging. Just let SharpCap do the imaging.
Yeah, but I want to make sure we're,
But you'll know in SharpCap. Just slew to it in Nina, and then we'll be fine. Yeah.
it got disconnected because
Yeah,
of it.
that's no fun. So change your exposure. Set your exposure to 5 seconds. If it stops slewing. See what it has. And then scroll down. Yep. And then where it's the red, click off that red and hit that button. Okay, that's not good.
No,
That's like noise. What's it pointed at then?
I don't think it finished slewing
Okay,
because,
that could be entirely possible. But it's not changing. Yeah, I think something isn't right here.
let me do this. Hang on. I think lost connection in one.
Let's do a 15-second exposure.
Yeah.
Okay.
I'm sorry, Bill. Oh, next link? Yeah, it's not even in the,
Okay, yeah, it's not pointed to where it should be. Okay. Yep, that'll do.
there
There
we
we
go.
go.
And that color is nice.
Yep. Just a 15-second exposure. I'm pretty sure it does the histogram. It stretches the histogram for that image too, which is fine. I think so, yeah.
Sure. Yeah. Thanks, Bill.
Here at the YMCA, we had some boards, so Bill will take those down. Telescopes are getting put up. We've had some telescopes outside because we had storms this morning, and we've had quite a bit of rain this past week. So the ground is wet. When the temperature drops, the humidity goes up, and now we've got dew on the telescopes. So once the optics dew up, there's not really much of a point in staying out anymore. They are being packed up. Pretty sure that Jim has some dew heaters on the telescope. So we have this issue everywhere. So what we do typically, and this is
Yeah.
more of a winter thing than a summer thing, but we have heaters that go around the telescope optics that we can control how much power goes through it. And it's a neat little device. It's a strap that goes around the telescope, and it warms up the optics just enough so that they stay above the dew point. That way, dew doesn't form on. We can also help prevent dew by using a long dew shield. So in the previous image, we could actually see that on the front of the telescope. It's basically an aluminum tube, attaches to the front, and it acts as a dew shadow. So if dew forms, it typically comes down, straight down, and if the optics are in the shadow, they stay dry. Now, if you point the telescope straight up, you're going to get dew on. At that point, you want the dew heaters. But the dew shield does do quite a bit to keep dew off of your optics on this type of a telescope. Don't know why it is saying re-slewing to target because it looks like it's dead on. I'm going to jump in here. So let's see what this thing's doing. Yeah, that'll work. Okay. I don't know if we've sharpened this thing up. I don't know if I don't think we've done the focus. So I am not too familiar with Nina. Stretching the image, plate solving. Now it's doing the solve. Status not found. Okay, what's it doing now? So it's taking the image.
It looks like it's okay. It looks like it's okay. So how do I disable this camera? I don't know. Load image, image source. What's this one? So what are we doing? Imaging. Go ahead. I haven't used Nina in a very long time. That's why I do everything in Sharpie.
Okay,
So I didn't turn off the camera, so
yeah, I need, yeah.
they need to do that.
Okay. Turn on the camera here.
Right. We did get it working. So we got to see Jupiter, we got to see Saturn. We're going to be looking at the Orion Nebula.
Wow. And how does that work? Like, where you are, so you are projecting here, but which telescope is capturing this?
The
The one
teles-
at the remote site.
Yeah, it's 150 miles away.
Oh, okay.
So hang on. So now we've taken the image and we can come here. It's probably easier if you go over there. That way you can see it on that screen. And this is
the same thing, right?
Yep. But we're doing a really fast, 5-second exposure. We need a much longer exposure. 5 seconds is not nearly enough. Let's start with a 15-second exposure. And let's see what it does. So this is the raw image. Okay. There's not much to see because the stars are very dim. The nebula is very dim. This is raw data from the chip. This is like the base. And what we have to do is stretch the histogram. We need more data. Lots more data. And we can see the histogram is here. This is black. This is white. Notice there's a lot of black, a lot of very, very dark gray, almost no white. Okay? That tells us that this is going to be a very, very dim image. So we do something called a histogram stretch, where we say, what is wrong with this? That's what we say. What is wrong? Gain is fine. Something isn't right with this. This is ugly. Okay. Let's get rid of that. That's still ugly. I don't know what's wrong with this. It should be a better image. So what we're seeing right here in the middle, this is the trapezium. And the trapezium is a small group of stars. They're hot, they're white, they're very, very bright, and they're throwing off all this UV radiation that is causing the rest of the nebula to light up. There is some setting on here that we're missing. I'm not sure where it is. LX mode 50. No, that looks fine. It should be raw 16. Everything. Hold on.
Should it
hold on.
be? Shouldn't
Hold on.
it be this?
No. It should be raw 16. Because we want 16-bit.
What
Try-
nebula is in the Orion, right?
Yes. This is the sword of Orion. Nope, doesn't like that. That's the black and white version. Let's switch it back. No, don't force it. Is
In this world.
I don't know if that's the right configuration.
It is.
Okay. Hang on. Nope, because I don't have my camera on. Want to try imaging through Nina and see if Nina does it any better? I don't like how this looks. I'm not really familiar with that camera either. Okay, can you just full screen that?
Pardon?
Can you full screen it?
Pardon?
Full screen.
I'd have to rip all this stuff out. Yeah.
There's no, yeah, there's a full screen button.
Good.
that not it?
That's full screen within
No.
there.
There's no full screen, full screen?
Probably the third
No.
button.
No. That's what third button
Ne-
was.
Yeah, so,
Great job, Nina. So what we're looking at with this is the Orion Nebula. All the dark places that you see, these are the dust bands. So these are places where the light is being blocked out. That there is nebula behind it. There's glowing stuff behind. There's stars behind this. But this is a black dust cloud that's blocking all that light. So that's what gives it this shape with these big wings. There's actually this dust band in between the reflection nebula that you see on the right and then the emission nebula that you see on the left. Actually, the one on the right is a is that a reflection? No, that is also a an emission nebula. There is some reflection nebula in there, but it's also emission. It's mixed. Nothing is ever one thing or another usually.
Yeah.
Well, no, I take that back. Some things are one thing and not. We have Pleiades M42, which is a reflection nebula. It is a cluster of stars that's moving through a dusty part of the galaxy, and the light from the stars is just reflecting off of that dust. There's nothing glowing, it's just reflection.
Is anyone controlling Disney telescope?
Hmm?
150 miles away?
Yep. Yeah. And this is what a lot of astronomers do now, that we can control telescopes remotely. For example, we have a number of very large telescopes on Mauna Kea in Hawaii. So the telescopes up there are at almost 14,000 feet. It's 13,800 feet or so. It's very, very lovely up there. It's very cold up there. And the air is so thin that they don't really let kids under 13 go up to the top to see the sunrise or the sunset. So when I was there, I had to go with a friend of mine instead of bringing my family because I had a 6-year-old at the time and he was not going to be able to go. So my wife stayed with him down at about 1,000 feet, and instead I drove with my friend up to the Viz. And at the Viz, we stayed for about an hour to get acclimated at 9,000 feet, and then we drove up to almost 14,000 feet to see the sunset. So the telescopes up there, because the air is so thin, visiting astronomers don't go up to the telescopes. They may go once or twice to go see them, see, ooh, wow, this is really neat, really big, this is really nice, I like this. But then they go down to the Keck, like specifically the Keck Observatory Center in Waimea, in the northern part of the Big Island. And that is at much lower altitudes, and that's where they do their actual work. So there are technicians up on top of the mountain who are doing the work of making sure the telescope is working, getting it into position, doing all that stuff. But the astronomers stay down at a lower level. They're the ones analyzing the data. So the astronomers typically aren't doing this where they're not sitting at a computer controlling the telescope anymore. They get the data afterwards, but they monitor it to make sure, yes, this is what I want to get. And sometimes it's a matter of, hey, there's something interesting actually just over here that we didn't realize was there. Now, well, maybe we'll just do this, take a look at that, and start analyzing. But there have been several discoveries from astronomers who are just imaging something that, just imaging a part of space that is nothing there, okay? There is one astronomer who is just found several objects, oxygen-3 objects, which we didn't know were there. The way he did it was he just took a very wide angle camera and was pointing it at different parts of the sky. And specifically, he was imaging the area around the Andromeda Galaxy.
And he noticed on some of his images that there was this kind of arc around Andromeda in oxygen 3 light, this blue-green color. And processed the images, and he found something which professional astronomers haven't seen in before. That's what it's describing.
Good trying. About 45 people. Oh, that's good.
So it's a brand new object, and it's named after him because he's the guy who found it. I believe it's called Falls 1. So it is
There we
this
go.
blue-green arc around Andromeda.
Good reason to get out of the house.
So it's something really neat, and he was an amateur astronomer, and he's gone on to find several others of these objects, and this is now his catalog of things that he's found.
I can't see it. It's like, yeah, what?
See, that looks better. I don't know why.
Well, partly it's out of focus.
It was. Oh, it's out of focus.
Yeah, we haven't done a focus run.
Can you zoom in on the very center?
All right, thank
Okay,
you.
thank you.
No.
Bye-bye.
Good night. Thanks for coming.
Thanks for coming. Young astronomers.
Zoom in at the zoom is at
Thursday, March.
zoom.
Oh,
Teach
Change
something
the
new every
zoom
month.
to like I don't know.
Teaching good.
Yeah, 200 should be good.
Yeah.
Okay, there we go. So that's roll out just a tiny bit.
yeah.
I don't
And
know why it's showing it that way, but what we're looking at right now is the trapezium. It's not quite in focus, or is that as good as the focus is going to get?
it's not in focus. We haven't run a focus run.
Okay. We haven't done a focus routine.
Chris, do you want that?
But right now,
Huh?
it's just background. So
You
Oh,
gotta-
no,
do we-
that's fine. You can
Yeah.
We'll break it down out
You
there.
can have it.
Thanks for coming tonight.
Thank you.
Yeah.
How many people did you have out there?
About 45, I think.
That's awesome.
So, yeah, it was good. It was good. Kept coming back and forth, so. I was
I'm
down there
I'm
10.
gonna do it. Gotta do it.
So
We're
it
gonna
was,
go to. We're gonna
so
go
I said, stand
to.
up by that farther path. So we tackled guys as they came by and said, you got any?
Uh,
That was the purpose, sitting all the way down there. It's like, you can't go by without seeing stuff. So probably got about 20 people that way. Well,
On, at the Cook's Hospital thing that you're gonna do,
uh-huh.
would you want me to try to round up some, little kids giveaway things for astronomy? Or space or whatever?
No.
Okay,
Um,
I don't know if they would.
no, that would not be a good thing because I could just see him going into mouths and
Sure.
stuff like that.
Right.
And they're moving us to the Hofberger Auditorium. So.
Oh, not the north.
Not the atrium.
Atrium,
Yeah,
okay.
so I don't know if we could even set up outside of the auditorium.
sure. Okay,
But if you brought these panels only, I'll talk to Megan on Monday and I'll let you know.
okay, sure.
Yeah.
It takes up about 13 by 3 or 4 feet,
Okay,
about 3 feet, about 13 feet wide.
okay. Is that the panels or the?
These,
top?
it's
13,
four
okay.
of these. and
Okay,
30 or 36 inches.
okay,
3 feet times, that's 12 feet.
okay.
And actually, you could put them above and below each other too.
Yeah.
Take up half the amount of.
So,
We can do a focus routine.
yeah, it's gonna take a few minutes.
Well,
Yeah. So let me do that.
we can see how it goes.
Let's
It is
see, the last,
8:30, so we've been at this for 2 hours. And honestly, sometimes this is what it takes. Like I mentioned before, I had been, sometime last week, I was trying to get something working, and I was working till from I think about 8 o'clock at night. After I helped my wife
4
put my
minutes.
kid to bed. And then I was working till about 12:30 at night, trying to get everything working. I started imaging about 11 o'clock.
nothing was working. My focuser didn't want to focus properly, which is a bad night image. But sometimes that's the way it goes, and I pretty much gave up and went to bed. I did not feel like wasting any more time that night.
The kid in me.
But wait, this is fun. I think this is fun. Not the slog of getting it working, but it's fun when you actually find your target and you're able to get some good images, and you can see some of the stuff that previously was just really hard to see. Oh, Wikipedia. I'm trying to bring up some images of M42, and that's just not working well. Let's see if I have my stuff.
That's going on.
Did you lose connection? Where is my lose the connection?
Pardon?
Did you lose the connection?
No.
You are doing that. Is it still imaging, or what's it doing?
Uh,
Or is it doing the
it's
focus?
focusing.
Okay.
Oh, it's almost done. Oh, it is done.
Oh, it is. Okay, cool. So
Yeah, we got much better HFR.
cool.
So let's
Start
find
imaging.
Uranus.
Uranus is, well, Uranus and Neptune are one of those things where it's kind of hard, unless, I guess if you do the plate solve, it should be fairly easy to find. But but they don't look like stars, they look like little disks. And with a telescope, looking with your eyeball, it's really, really obvious that the planets stand out. Uranus is a little pale blue dot, and so is Neptune. It's even smaller. But it's really, really obvious because the stars are tiny and they twinkle. The planets don't. You look at it, and no matter how much you try to focus, it won't go down to a point. It's always a little disk.
We'll just slew, see if we get it in the area.
In the meantime, let's see if I can do this. See if this works. Ah, here we go. All right, so we've gone back to the telescope at our dark sky site. That is Uranus. Is it impressive?
Nope.
Not terribly.
What?
What's really neat about this is if we do the lucky imaging with slightly longer exposures and we process those images, we can actually see the moons. So I'm going to go see if I ever do anything with them. Remember if I did, I'm going to go look for it. Let's see. Where did I put it? That's that. I had an image, Uranus somewhere. I can't remember where I put it. See if I can find it. Yep, so Uranus is really small. And with the proper exposures, you can find the moons. So I'm looking through my archive of images. I don't see it. No, I don't see it. Okay. I am not at my office desk, so I don't have access to all my images, just a couple that I uploaded. No, yep, no Uranus here for me. And what I would like to do, and I did it a while ago. I have an RSpec diffraction grading filter, and I can put that onto a camera. And when I do, I can actually take the spectrum of a planet or a star. And if you do it on Uranus or Neptune, you can actually see the methane lines. So we can determine what gases are in the atmosphere of Uranus. And the way we do that is just by reflected light. So we measured the light coming from Uranus, and the sunlight that hits the atmosphere of Uranus will absorb certain wavelengths of light associated with certain elements. So we'll see these, what we call dropouts. We can see these dropout lines for methane, as well as other gases. And that's one way that we can determine what elements are in the atmospheres of other planets, even other stars, is by looking at their spectrum. And it's actually astronomy that you can do with your own equipment.
We're going to Neptune next. And we're going to go to Higson 97, which is right next to Neptune.
What?
We're going to go to Higson 97 right after we go to Neptune.
Okay. And for anyone wondering, because it is a dark image out there. Let's see. I have an image of two telescopes, which pretty much the setup that we have out there. Why, here we go. That's all. That's for Neptune? Okay. While it's doing That's kind of jumpy.
Yeah. Yeah. Okay, so,
Or no, or is that the plate saw?
yeah, I place all,
No, I
so,
mean, that's the writing. It from our view here, it looks like the it's jumped. But if you zoom in, I guess that is yellow text.
yeah, yeah,
from the
it's
place saw.
just the HRR value, so I'm gonna disconnect the camera. I don't think we need 2.5 seconds, so maybe we need more than 2.5 seconds.
It's jumping around just a little bit.
Yeah,
Want to zoom in some more?
yeah.
No, not ROI, zoom.
Oh, oh. I've got ROI on my mind at the moment.
Oh, okay, fine. No, you've got. I guess the ROI was fine. Just wanted to zoom in so
Yep.
it looks bigger. You're not centered. Now zoom in like for 200%. That should be fine. Okay, a little bit
Hey,
more.
Bob.
Hey,
Hey, Chris.
Maroon.
Hey, I think the other Chris Kumal, is that his name? I think he's left his chair. I wonder what I should do with that. One of the, the lawn chair kind of thing. I can take it and then probably let him know. I think
Yeah, I
Take
would.
it, bring it to the meeting.
Okay.
And then
Yeah.
post on the e-group saying, hey, I got your chair.
So there be Neptune.
Looks kind of oblong.
It does.
Yeah. It probably should.
It's probably seeing, honestly.
What is that?
Neptune.
Let me take a picture of it. Is it okay if I take a picture of you guys?
Yeah.
Sure.
Fly ones.
Not
I-
responsible for broken cameras.
Find the camera. We're live on YouTube.
Oh, okay.
So I'm going to go ahead to Hickson 97,
Okay.
which is a group of galaxies
All right.
very close to the area of Neptune. Should fit nicely in this frame.
Is there a camera rotator on there?
No.
I mean, there's probably a manual camera rotator.
Hmm?
Probably a manual camera rotator.
Maybe, I don't know.
You undo the little set screw and you turn your camera.
Yeah. Yeah, Maru's going to take care of it. Thanks for coming.
That's great.
Thank you. Thank you. I really appreciate it.
Jim says it's the tennis shoe rotator.
Pardon?
Jim says it's a tennis shoe rotator. You walk out there in your tennis shoes and you rotate the camera. I like to call it yogurt powered. That was John Dobson's term for his Dobsonian telescopes. Is they're yogurt powered. You eat some yogurt, gives you the energy to move the telescope.
Ours isn't up yet. So we've seen all the planets that we want to look at.
Mars is too low.
I don't think it comes up until later.
Doing a plate solve right now?
Yeah. Did I not? Yeah.
No, it is plate solving and no, it's doing an exposure to find out if it's pointing at the right thing. That is, can you set it for a shorter exposure?
Yeah,
For
but
plate solve?
it's set to 15. There we go.
Okay. I'm just curious, with sharp cap, I can usually do a decent plate solve in like a 2 or 3 second exposure. The only issues I ever had was if I was shooting at f10 for a really, really narrow field of view, and then I had to go download the much, much bigger data sets, and it took a lot longer to do the plate solves.
See.
Is that it?
Can't tell, honestly. I think so, but I'm not sure. Not sure. Yeah. I think so.
Okay. So,
Not something we'll,
all right, well, we need much longer exposure now.
yeah, but that's okay.
So with galaxies especially, you can see just a little bit with the shorter exposure, but it's pretty much just a little blur.
Let's see. What else do we?
Well, zoom in. Let's see what we can see.
I'm sorry?
Zoom in, see what we can see. Unless you want to do something like a big globular.
Yeah, let's see.
All right, let me see what I can find.
M3.
It's a good globular. We have the rosette is up. That's not going to be easy to see.
Oh, M31 is up.
Messier 79 is a nice little globular. It is just it's lower in the lower in the southern sky. Let me see what's up high. Pleiades up there, Messier 34. Andromeda. 2 is an open cluster.
Oh, M31, of course it's up there.
Yep.
Um,
Angulum. 74. Where is a good clock? M79. M79 is a globular. Is M13 up?
It's going to be too low for us.
It is? No, okay.
Yeah.
It's reflection. 34 is an open one. That's at near zenith. Oh. Double cluster is going to be too big. Okay. Oh. Well, no. Should be able to do M13.
M13 is too low.
Is. Oh, yeah, you're right. Never mind. Way too low.
Yep, we're almost done.
You going to kick us out?
Hmm?
Are they going to kick us out?
They close pretty soon.
It is almost. Oh, it is. It is 9 o'clock. Now, if I was at my house, I'd be doing this about 1 o'clock in the morning.
Yeah.
But
So,
I am a glutton for punishment.
hang on, let's do it this way. Cheap little bit.
Looking for a globular cluster. No. Cetus A. It's a galaxy. Open clusters, dark nebula. Open cluster. Don't see any globulars up right now. Within that one's pretty low in the sky. Messier 68 in Hydra, but doesn't rise until 1 o'clock or almost 2 o'clock in the morning. That's not going to work. Oop. Messier 3. A lot of the stuff won't rise until late tonight.
M33 is going to be way too big.
Okay.
But Horsehead might frame nicely.
Let's see what this one is.
Let's see.
We're
here.
looking towards the south.
I
Oh,
see.
how about this? NGC 1535. It is a planetary. NGC 1535, a little planetary. It is near Orion. It is not quite due south. We should be able to hit it. About the same altitude right now as Rigel. A little further to the south. Or I should say to the west of Rigel, not to the south.
NGC 1535.
1535. A little planetary.
Little, yeah, like,
Eh.
looks like kind of like a donut maybe.
Yep, 0.8 by 0.7 arc minutes.
How many people are still online?
Oh, still have 7. Hubble's variable nebula. I don't know. It's pretty variable. Could be good, could be bad. So doing the plate solve right now.
Yeah.
Not taking a long exposure. Can you change it? Or is that just
That's what Jim has it set.
okay? Yeah. Let's not mess with someone else's imaging train. Thinking the scope. Plate solve, it realizes that it's not pointing at what it thinks it should be pointing at. So let's send the new coordinates to the mount on where it really is pointing and have it go to where it should be. They will kick us out of the YMCA fairly soon, so this I think is probably the last object we'll see. We'll do one more.
Oh, yeah, it's almost centered. Pretty small.
Oh, down below?
Hmm.
Yeah, but Jupiter's also pretty small too, so how about that size? So once it centers it, should be able to see it pretty decently. Even with the 15-second exposure. There it goes. Hey, it's bright, it's blue. I don't think it has a name. I will double check what this is called.
A bright and blue dot in the sky.
It is NGC 1535. It is a planetary nebula in Eridanus. And it has, now let's look it up. We have internet access, that's what it's there for. So NGC 1535.
All right.
Cleopatra's Eye. So it does have a name.
The Sultrus of Sultrus.
It was discovered by William Herschel in 1785, and it's similar to the Eskimo Nebula in color and structure, but the center star can be quite difficult to observe visually. Maybe we'll see it if our focus is good.
I'm gonna guess we're gonna need more than 5 seconds.
Yeah, scroll down. Hold on. Hold on. Leave it at Okay, do 15, but scroll down and let's change the image properties because I'm pretty sure it's set for raw. Keep going down, all the way down. Keep going all the way. Oh, all right, let's then finish taking the image and then we'll do the histogram stretch. This doesn't automatically do it. Okay, there we go. So hit the histogram stretch. Okay, well, that looks so ugly. I don't know why it looks so ugly.
I don't know what's going on.
I don't know either. You know what? Hold on, hold on. Let's do this. I'm wondering if there's something with the. Just wondering if something, if this was trying to do something. I don't know why it would. Yeah, something about this. This just isn't right. This isn't right. It should look a whole lot better.
Mhm.
Mask over. Let's do this off. None. No banding suppression. There's no darks. I don't know why this white balance. There we go. See, that looks much better. That looked okay. There we go. Do that. See, that looks a lot better. That's a whole lot better. And that bright dot right in the middle,
Yeah.
is that the central star?
Yep.
Could be. See, now we're seeing the noise.
Yeah.
Now we're seeing the noise around it. Okay, let's do something else. Hang on. Because this is what I've been messing with. I do the background subtraction, and I did the low frequency wave. It usually clears it up really, really nicely. Let's see if this works. Hey,
Yeah, that's nice. Yeah.
it's better. All right, we got Cleopatra's Eye. That's actually pretty decent. Okay, yeah, we are seeing a lot of noise, but that's because it's one image. So if we want to clear up the noise, we take a lot of images, 50, 100, 200. And this is only a 15-second exposure. Do a 30-second exposure. Let's see what happens. Scroll all the way up. Ooh. So we do a 30-second exposure, and at the same time, scroll all the way down. We wait. We hit that auto stretch locked. See what it does. 30 seconds. So we get more data in 30 seconds. We auto stretch it out again. Yeah, we can see a little bit in there. So if we look at raw data, yeah, there's almost nothing in there because most of it is deep in there. Auto stretch it. Oops. Auto stretch it. Now we can at least see the halo. We can see the inside. And if we process the data, we should be able to see more detail in the core. But again, that takes time. That takes a lot more images. But hey, we're able to see stuff we couldn't see before. Interesting. 5 people still on. You get to see Cleopatra's Eye. Oh, and the stars.
Yep.
That's pretty neat. You can actually see the stars in Europe.
Let's do the last thing. Let's look at
What are we looking at?
look at the horse head.
Look at the horse head. Okay.
I see 4. It may not fit, but we'll give it a shot. 4, 3, 4.
If you like your classic science fiction, the Horsehead Nebula in Isaac Asimov's this old book, The Stars Like Dust. So he doesn't call it the Horsehead Nebula, he calls it the Horus Head Nebula. Because in the rest of the galaxy, the story was that the first person to go to that nebula was Horus Head. So it's called the Horus Head Nebula. And only on this backwater planet called Earth do they say no, it's actually the Horsehead Nebula, because from Earth and Earth alone, the nebula looks like a horse's head. I really, really liked that story when I was a kid. I first read it. And all of these nebula, everything that we see, that we name it from our perspective, what it looks like from Earth, what it looks like to our eyes. And we are pattern-seeking animals. And so we look for patterns. We look for things that look like what we're looking at. So the first people to look at the Horsehead Nebula in images thought, well, it looks like the profile of a horse's head. So it is the Horsehead Nebula. So what's it doing right now? It's just slewing?
No, it didn't center. Now we're going to slew. It went to NGC 2023, not actual Horsehead.
So because of the long focal length on this telescope, we'll see just the Horsehead.
Yeah, in NGC 2023 here. Yeah, get a nice little 2-panel on the flaming bush.
Now it's imaging to do a plate solve. Yes. We can barely see it in there. And it's upside down, which is fine. Our orientation in camera doesn't matter very, very much, especially if we can always flip it once we actually do the processing. Earlier this year, or last winter, we were at Thompson down in Keene. We were able to image, or I was able to image the Horsehead through the C14. It was very, very, very tight, but we can see pretty well. So that looks like it's centered. We're close enough to it.
Raise up by 5 seconds. Let's get 1 minute.
There it goes. Okay. Is it now ready, Tim?
It is. Okay.
Okay. I think it's taking the last option, so 15 second, 30-second exposure. You want to take the ROI and make it bigger?
Yep.
Yeah, maximize it. Oh yeah, we're gonna have to. Oops. Scroll down and we'll do the Instagram stretch. Don't want to do anything right now. Take the last one. Hurry up and wait. Right. Downloading. There it goes. Okay. Stretch the histogram. Did it?
Good.
Okay. Can we see anything?
Yeah.
Yep, there it is. It is just barely there. Okay. So it's got one frame. So this is the live stack. So this lets us get better images. It just takes a little while to do. So it will take it will take the images and then it will stretch them out. Not sure why. That's something real fast. Uh, so what happened there? That's just blown out. Okay. Yeah, push it back. Other direction.
It's interesting.
Yeah, that's the. It just needs darks
Yeah.
and flats probably, and bias.
And yeah, we have that actually.
Well, it's fine. We can actually make out the shape.
Yeah. Stars look pretty good.
All the stars are fine.
Actually. Yep. I gotta remember where we got them.
Better.
Yeah.
Kind of dark.
Yeah.
Okay.
And we've got flat too.
But not a
Yeah.
lot.
What you need us to back up? What time y'all close?
We close at 6.
Oh,
It is
well, guess what?
9:24.
We'll pack up right now. Thank you.
All right, so we have the horse head, and I guess that's going to be the last thing that we're going to see today. So what do you think, Bob?
We did okay. We got some process errors to figure out. But I think I know what the initial error was. Now it's an operator error.
Okay, well, it just took a little while to get that fixed, but now that we have it down, there's a process. I think we could probably get away with doing almost everything through SharpCap, especially for the Raza being out there. And it just may be easier to do it there.
Yeah, well, I'll experiment with it
Yeah.
tomorrow.
With my workflow, the way I do it for mine, it seems to be pretty easy. I'm using Starry Night Pro as
Mhm.
my what am I pointed at?
Yeah,
thing.
and I've actually had that.
Yeah, and with the iOptron, it makes it really, really easy. Yeah, I'm able to do all my stuff pretty quickly and like solve pretty quickly, and I don't have to keep jumping between applications.
Yeah.
Nina is a very powerful tool, but I think Nina is really more for imaging and not really for
Yeah.
EAA. But that's fine. Okay. Want to say goodnight to everybody? Bob,
Oh,
camera, you can say
I'm sorry. Good night, everybody, and thank you for attending. Have a great day and Happy New Year's.